Guys, welcome back. We are continuing on converting Cartesian integrals, triple integrals to, in this case, now spherical coordinates. And here is our problem where we're looking at 0 to 3 with respect to y, the integral from 0 to the square root of 9 minus y squared with respect to x, and then the integral of the square root of x squared plus y squared to the square root of 18 minus x squared minus y squared with respect to z of x squared plus y squared plus z squared. And the first thing that I'm just going to acknowledge here is the fact that we already know what x squared plus y squared plus z squared is. We know that that's going to be rho squared, so we're going to go ahead and just write that out. All right, so in the previous video that I just did with you guys, the thing that I suggested doing is writing out that z, being the innermost integral, is equal to these two equations. So let's play around with these two equations for a second independently and see what we can figure out based on this bounds. So we get that z is equal to 18 minus x squared minus y squared. So if we want to square both sides, we get that z squared is equal to 18 minus x squared minus y squared. And we finally, if we move the x squared and the y squared over, we get that x squared plus y squared plus z squared is equal to 18. Well, we've been here before, friends. We know now that rho squared is equal to 18. And so rho is going to be equal to the square root of 18 or 3 squares of 2. So this is telling us that rho is going to have an upper bound of 3 square roots of 2. And so that's pretty awesome for us to do. So we know that rho is going to be from 0 to 3 root of 2. And the reason the rho is 0 here is the fact that our x and our y values are going to also be at 0. So we'll talk about that here in a second. All right, so then let's look at the other one. Let's dissect this next equation here. So we get that z is equal to the square root of x squared plus y squared. So we get, when we do the square root, we get z squared is equal to x squared plus y squared. So I have actually did this in example number 5, and I'm going to use my scroller up here to show you guys that when we did that, right? So when we did this, we had the equation of z squared equals x squared plus y squared. And through all this work, we found that phi is actually pi over 4. So we're not doing that work again. It's there for you. So that is what we're going to say about this. That all is said and done here, we're going to get that phi is equal to pi over 4. So this is going to tell us that our bounds for phi is pi over 4, 0. So then what we're going to do now is look at our change with respect to x and our change with respect to y. So we kind of had a conversation on the last example where when we're doing these examples, we get that x is equal to the square root of 9 minus y squared. And so when we square both sides and move the y over, we do get a circle of radius 3. However, we're going to remember that since it's the positive of x, we only want the positive x version of this, right? And we actually had this conversation in the last example. And then since this is a radius of 3, right here, just like in our previous example, my friends, is to send that y is going to be from 0 to positive 3. So that means, and this is what's going to give us our theta, right? Our theta aspect of this. So that means that theta is going to be from 0 to pi over 2. All right. So what this, and by the way, we're starting here in the center. That's why our 0 for rho and for phi. So when we do this problem, we're going to now go ahead and start writing up what our answers are for this. So our basic integration is going to be from 0 to pi over 2. Um, 0 to pi over 4. And these are going to be interchangeable. So then we have 0 to 3 over 2. Then we have rho squared. And then I did this in terms of rho. And then I've switched it up this time. Usually I do theta next, but I did it in terms of phi and then in terms of theta. So again, these are interchangeable. Okay, so that is all we have to do for this problem, and there we go. So something very complicated, as you see, Cartesian is much easier for us, and that's why we like to do these conversion factors, because this would be a nightmare to integrate, and this right here would not be bad at all to integrate at all. And if we were to integrate this by hand, we would just split them apart like we did in the previous example, I think with example number 5. So that's all I got for you guys for this video, and I will see you in the next one. Take care.